Good evening, everyone. Hope you're doing well. And here's our final lecture before the Thanksgiving holiday for those of you who are observing Thanksgiving. And this is the third of our lectures on global climate change. Going to try and wrap things up. And as I've already mentioned, tonight I'm going to look at the other potential influences on global climate. We've talked about greenhouse gas emissions. We've talked about the greenhouse effect and how it appears to be correlated with the warming pattern that we're seeing. But I don't want you coming away from this class thinking that I'm only giving you one side of the story, that I'm only showing you one set of data, that I'm not looking at the various alternatives that we would want to look at in order to make sure that we are addressing all of the factors that are impacting climate. And what we're going to talk about tonight is a variety of things that actually do impact climate and have changed climate for millennia, for going back millions upon millions of years. That's not the question. The question is, do those other factors explain the warming pattern that we talked about in our last lecture? So, with that in mind, this is the pattern that I'm talking about. The warmest years on record since 1880, where prior to this year, the 10 warmest years on record since people have been recording this are all in the preceding decade, which is a very strong pattern and rather a frightening pattern. And as we've seen, this does correlate or does track with the amount of greenhouse gases, carbon dioxide particularly, that humans are releasing into the atmosphere on a regular basis. And this appears to be continuing. As I've mentioned, we are in late November, and 2025 is currently on track to be either the second or third warmest year on record. And as you are aware, this coming weekend, we are expecting a relatively warm weekend for November. So the pattern appears to be continuing. But remember, as we've discussed, it's global averages, not just what's happening here in Southern California. So we need to take all of that into account. And when I say we, I don't mean me. I study fossils. But in terms of climate scientists who are analyzing these data, this is what they are currently projecting. And then probably early next year, we'll find out whether or not 2025 was in the top two or three warmest years on record. So let's look at other things that can impact Earth's climate and whether they can match the pattern that we just talked about and that we talked about last lecture. So let's start with an easy one. Let's talk about where the energy is coming from. It's solar energy. And it is true that the sun fluctuates in the amount of energy that it is releasing and the amount of energy that reaches us here on Earth. You have solar minima and solar maxima, and they can be discerned by a variety of sophisticated instruments that can measure the amount of energy reaching the Earth's surface. But if you have the right equipment, you can also tell at a glance, because solar minima are characterized, as you see here on the left, by virtually no sunspots on the surface of the sun, whereas solar maxima are characterized by the presence of a few to many sunspots. That's an important point, and we'll come back to that. I will probably test you on this, though, that periods of increased solar energy output are correlated with an increase in sunspot activity and sunspot visibility. I will probably test you on that. Now, this is a graphic showing when we've had the past several solar cycles. We're currently in cycle 25, and you can see that over on the right, and then cycle 24, cycle 23, cycle 22. So if these peaks in solar energy output correspond with the warming years that we just talked about, then maybe this explains the pattern that we're talking about. So with that in mind, let's go ahead and plug these in and see what we can come up with. And hopefully you're noticing right off the bat that there isn't a pattern. You don't see the warmest years on record correlating with peaks, except the two most recent, where they are coincident with the current peak. And if the projections are correct, in 2025 is also going to be among the top three warmest years. It's also meeting the projected peak for cycle 25. But the rest of these are not. So, what you could imagine right now is this rejects the hypothesis. This rejects the idea that solar energy output is responsible for the warming pattern we're seeing. Now, I want to be devious a little bit here, and I want you to think about things. I want you to look at this pattern and wonder if there's any other way around it. And what I'd like you to do is think about our year. And what are the warmest months of the year? Generally speaking, here in the Northern Hemisphere, here in Southern California. Because the one day of the year when you have the most sunlight in the Northern Hemisphere is what's known as the summer solstice, also known as midsummer. It's the longest day and the shortest night of the year. And this is when we have the most sunlight hitting the earth. And it falls between the 20th and the 22nd of June, and it marks the beginning of summer. So keep that in mind. Every time from now on, when you hear about it's the first day of summer, that means that it's the summer solstice. The sun is directly overhead in the northern hemisphere, and it is when we are going to get the most sunlight for the year. And so you might imagine that that means that would be the warmest day of the year. And yet, as you probably know, that is not the case. This, once again, is showing not just this year and the past couple of years, but all of those gray squiggles are the years going back all the way to 1940. And, excuse me, yeah, you're seeing 1940, and you can see that here is generally where you see the peak in the warmest temperatures during the course of the year. It's in July and August, and in Southern California, frequently extending into September. It's not June. Things continue to get warmer after June, after the longest day of the year. We see the same thing in ocean temperatures, where there's actually this valley, this drop in ocean temperatures around the time that you might expect it to be as warm as possible. Okay? So something is going on. And you don't need to look at the year to see this. You can see this on a daily basis. This is actually, I looked this up just for you, and this is the forecast for tomorrow here in San Bernardino. And you can see that this is noon, and this is when the sun will be at its peak. This is when we will be getting the most solar energy. And so this is when you might expect it to be hottest. But you are probably aware that that's not the case. If you pay any attention to daily weather at all, you're aware that it's after noon when you hit the highest temperatures. Even though the sun is starting to go down, or more realistically, the earth is starting to turn away from the sun, nevertheless, the temperatures seem to increase. So, what's going on? And if we can figure out what that is this pattern something to do with what we might be seeing with sunspot activity and solar energy output? Well, what's happening is while the sun is up, while it's going up in the sky, and when it reaches its peak, the earth is absorbing that energy as well. And we've talked about that. That's one of the manifestations of the greenhouse effect. Remember, we talked about some solar energy is reflected back into space. Some of it is absorbed on its way in by the atmosphere, and about 50% of that is then absorbed by terrestrial and marine systems. And then about 5% of that is reflected back out, which adds to the warming that is coming in. And so, in an annual basis, you have that continued reflected heat. You have warm nights, so you're not cooling down as much because of that reflected heat. And so you have July and August and sometimes September being your warmest months, even though your longest day was in June. In terms of daily temperatures, you have that reflected energy maintaining and increasing temperatures even after 12 o'clock noon, because that energy is being trapped and it's driving up the temperature. So that's pretty standard. Could it be that something like that is at play with, there's the 5%, something like that is at play here with these, where maybe there's some lag, there's some built in lag? Well, it doesn't appear that that's the case, number one. And number two, if it was the case, keep in mind that this is cycle 22 through 25, which should suggest to you that there are a whole bunch of cycles that came before, and that is absolutely true. So if this was something where there was some kind of lag, then in those earlier cycles, and here I'm only going back to cycle 18, back in 1945, you would expect to see some of those same warmest years on record. you would expect that solar energy output to be manifesting over multiple decades, not just in the past 2 or 3 decades. In fact, you can see cycle 24 there, um, accompanying some of the hottest years that we have on record. Cycle 22 and 23 were much more severe. Cycle 18 and 19 were even more severe. So you would expect those higher temperatures. Whether or not they correlated directly or there was some sort of lag built in, you would expect to see that pattern. And we don't see that pattern. So it would appear that what we're looking at is recently focused over the past few decades and not something that extends backward in time. And in fact, scientists have determined this, where if you go back to 1880 and you can see the fluctuations there in yellow of solar irradiance, the energy being released in all of those cycles through time, and you can see how it does not track the temperature here on Earth, which is a steadily increasing red line, particularly increasing around the year 1960, while solar energy is kind of fading off on the side. Not that you need to worry about the sun going out anytime soon, but there is no correlation here, at least back to 1880. Now, I've already mentioned the phenomenon known as sunspots, and I want you to keep those in mind because what sunspots are indications of increased solar activity, which might not make sense to you. So I will probably test you on this because they're darker than the rest of the sun. And so you'd expect if it was darker, it's maybe a little cooler, and so it's emitting less energy, and that's actually true. But we can trace what's going on with sunspots thanks to Galileo, and we can go back in time because when he was using telescopes back in the early days of telescopes, he and other astronomers were documenting the presence of sunspots on the solar surface. And so when we see those sunspots increasing, what we see is, by inference, comparison with today, we propose or we infer that what you're looking at is periods of increased solar energy output, which is what you would expect. Because with sunspots, you have those darkened centers, but then around them you have brighter areas called faculae. I may very well test you on that as well, just because it's such a cool word. And the thing is, faculae, even though the sunspot itself is emitting a little bit less energy, the faculae are emitting more than enough energy to overcompensate for that so that there's a net increase in solar irradiance or solar energy being released. And because of the documentation of Galileo and other scientists using telescopes in his time, we can now extend sunspot observations and with the presumed correlation with increased energy output back about 400 years to about the year 1600. And so what we can see is going back in time to a period between 1600 and 1750, there was a prolonged period of very little sunspot activity. And then around 1750 or so, you start seeing the cycles that we have already talked about, where we are still in some of those cycles. We're still going through those cycles. Solar cycles take place about every, I don't know, 10 or 11 years or so, where you go from warmer to cooler, and so on. Okay. Now, what you might also be noticing here is over there on the left, that thing called a Maunder minimum, which was a period of very little sunspot activity. And for whatever reason, it was thought to be um, a period of less solar energy. And then in the middle of the graph, you see a bunch of very low peaks there. That's the Dalton minimum. So you can have minima like these that are prolonged outside of the overall 10 or 11 year cycle of solar energy output. You might be asking yourself, what happens if that happens again? What happens if we have another unanticipated minima that comes up where the sun stops emitting energy according to the same cycle that we're used to observing? And scientists have actually looked at this and determined if that were to happen, we would still see a strong increase in global temperatures. It wouldn't be quite as severe. What we're currently looking at is the squiggly red line. If we were to have some sort of grand solar minimum Not a solar minimum like part of the 10 or 11-year cycle, but a bigger minimum, a more prolonged minimum. It might drop temperatures a little bit, but the overall trend would remain the same, and we'd continue to see warming temperatures here on Earth. So, solar energy does not explain the phenomenon that we're seeing. What else can we use? Well, let's go ahead and think about other things like volcanic activity. Can volcanoes contribute to global climate? And the answer is yes, they absolutely can. And we know this because of events like the eruption of Mount St. Helens back in May of 1980, which kicked a fairly large concentration of volcanic dust and gas into the Earth's atmosphere. And we have volcanoes that are doing the same thing today. Um, and what happens is not warming, what happens is cooling, because you have a net cooling effect. Here in the troposphere, you have some net heating up in the stratosphere, but down here you have a net cooling effect. And so, because of all the debris being kicked into the atmosphere, it reduces the amount of solar energy reaching the Earth's surface, and so temperatures drop. And so, this was observed with Mount St. Helens and documented. And as recently as 2015, the United States Geological Survey has commented on that. And they talk about how the carbon dioxide released in contemporary volcanic eruptions has never caused detectable global warming of the atmosphere. All studies to date of global volcanic carbon dioxide emissions indicate that present day subaerial and submarine volcanoes release less than 1% of the carbon dioxide released currently by human activities. So, in terms of the warming pattern that we are trying to explain, volcanoes don't explain it. And in fact, when you have volcanic eruptions, depending on their size, they cause the opposite effect. In fact, if you go back to the year 1816, which has been called the year without a summer, it's been called that because of the eruption in 1815 of Mount Tambora down in Indonesia, where it kicked massive amounts of debris into the atmosphere and essentially slowed down photosynthesis, reduced solar input. You had a lot of beautiful kind of yellow colored skies, and painters got very excited about that. But you also had famine and crop failure and outbreaks of disease because of the lack of a warming season in 1816. So that was the year without a summer. Things weren't all bad. Oh, I should mention this is a paper from 2019 that determined that it was an assumption. It was an assumption everybody was making that the eruption of Mount Tambora was responsible for the year without a summer. But this is actually a model that talks about getting the actual physical data, and they confirmed that that is actually the best interpretation. It's the strongest interpretation is that that volcanic eruption and the debris emitted by that volcanic eruption caused a global drop in temperatures. And I was about to say that doesn't mean everything was bad, because it was about the same time at the Villa Diodati near Geneva that an author named Mary Shelley, confined to the house in miserable conditions because it's not a very happy summer, because it's the year without a summer. So, with little else to do, she started a novel which eventually became Frankenstein, the novel you all know and love. Or for those of you who are more recent, Frankenstein, the novel you all know and love, currently on Netflix. No, I do not make any money for recommending this show. I haven't even seen it yet. Sorry, I've been busy with other things. Now, volcanic activity is one phenomenon that is part of a larger force at play on planet Earth, and that's the force of plate tectonics. And so, here too, we can look at this and see whether the movement of plates, which we have talked about multiple times this semester, might be having an effect on global climate. Because you have the plates moving against each other, directing where the oceans are going, directing where warm ocean currents and cool ocean currents are going. In fact, here's a map of ocean currents. And if you remember our lecture on Monterey Bay, you remember we talked about the California current and how it is a relatively cool current flowing from northwest to southeast along the California coast. And you can see that right there. There's the California current. Okay, so consistent with what we talked about earlier. And then you have currents marked in red, which are the warmer currents and so forth. So, where the continents are located is determining where those currents flow, and that determines where temperatures are distributed by the ocean across the planet. So, for example, if you go back about 3 million years ago, maybe a little more, North America and South America were not connected by dry land. And so you had Atlantic Ocean and Pacific Ocean waters mingling, and warm currents and cool currents mingling. And that's what you see here. And then around 2.8 million years ago, you have the connection, the land connection, and suddenly you have those warm currents are not making it over to the Pacific. They are staying over there in the Atlantic, and now they're being deflected northwards and becoming what we think of today as the Gulf Stream. It's a strong current, and it occurs today as a warm, northwardly mobile stream or ocean current because of plate tectonics. Prior to 2.8 million years ago, you didn't have the Gulf Stream along the eastern coast of North America, and today you do. This is also a period that I get excited about because you had any number of animals, Ice Age animals in South America, like ground sloths coming here to North America once they had dry land to walk on. You also had horses and saber-toothed cats making their way into South America and establishing a presence there. So it's called the Great American Biotic Interchange. I may or may not test you on that, probably not, but you might want to write it down because you never know. I might pull a fast one on you. But as a paleontologist, that's why it's an exciting period of time, and I get very worked up about it, just like this guy. Anyway, the point is, the Gulf Stream is a warm current that goes up the eastern coast of North America and then crosses the Atlantic and brings warm temperatures over to relatively warm temperatures over to Ireland and Great Britain and that neck of the woods. That's where the warming temperatures come from. And you can see this as an example, and I might test you on this because there are two towns or communities noted on the map: Hopedale in North America and Stornoway over there in the British Isles. And they're at about the same latitude. But Hopedale, the annual average temperature is about 28 degrees Fahrenheit. Stornoway, the average annual temperature is about 48 degrees Fahrenheit, 20 degrees Fahrenheit warmer. That is because of that Gulf Stream and the North Atlantic Drift. It's because of those warm ocean currents carrying heat, carrying energy into that area and keeping those temperatures relatively warm. Now, keep in mind, as we just discussed, the isthmus closed about 2.8 million years ago, which means this pattern we're seeing has been ongoing for about 2.8 million years. It is not something confined to just a few decades. So while this is definitely affecting global climate, it is not explaining the pattern that we are trying to explain with recent warming over just the past few decades. Oh, sorry, that's me at Stonehenge. I'm bragging about having been to Stonehenge. Um, this is Mount Everest. This is not my picture. I found it online. But I want to talk about Mount Everest because Mount Everest exists as a consequence of plate tectonics. It's mountain uplift where two tectonic plates are bumping and grinding against each other. It is the tallest point on Earth. And if you look at a geological cross section, you may remember earlier I showed you some geologic maps when we were talking about geologic resources and air resources and so on. This is a cross section of the geology of Mount Everest. And what you were looking at there, what I want you to particularly focus on, is the yellow areas that are labeled YB. And YB means yellow band. It's not terribly original, but that's what it is. And if you are climbing Mount Everest, you are going to, at a couple of different points, encounter that yellow band. And the reason I'm emphasizing that yellow band is because it is made of limestone. And limestone, as you know, is an ocean rock. The reason the Himalayas have been uplifted is because about 71 million years ago, the Indian subcontinent, which used to be free of the Eurasian plate, it was moving northwards, and eventually, about 38 million years ago to 10 million years ago, it starts really bumping up and squeezing into the Eurasian plate, and it is still doing that today. it is still pressing upwards into the Eurasian plate, and as a consequence of that tectonic activity, you have the uplift of the Himalayas. Now, as we've discussed, we're looking at limestone, and we've talked about limestone before. We've talked about cement manufacture and limestone and what is derived from limestone. It's a marine rock, as we've discussed. And what happens is when you have carbon dioxide and water mixing in the Earth's atmosphere, which is normal. You have carbon dioxide in the air, you do have water vapor in the air, and when they mix, you can form what's known as carbonic acid. And when you intermix carbonic acid with limestone, you cause chemical weathering, which is why the Sphinx looks so badly weathered, why it's so withered down. It's because it's been exposed, even in dry desert areas, it's been exposed to carbonic acid in the atmosphere, and it is very slowly weathering away. And one of the products of that is a slurry known as calcium bicarbonate. Okay. And what you want to look at there is that you've got carbon being trapped in calcium bicarbonate. It's in the name. So when the slurry forms, it is taking carbon dioxide that was in the atmosphere and it is trapping it in that calcium bicarbonate. It's essentially removing carbon dioxide from the Earth's atmosphere. And so that process that I talked about with the Sphinx is also happening with Mount Everest, where erosion is taking place. There is an interaction with the atmosphere. There's the formation of calcium bicarbonate, and that is trapping and removing carbon dioxide from the Earth's atmosphere. And then, as erosion takes place and those sediments wash down the hill into the river and then down into the ocean, those sediments carry that carbon dioxide with them and they bury them in the ocean floor. And so that is removing carbon dioxide from the atmosphere, removing it from the system entirely, and storing it in underwater marine basins for however long they will remain in the ocean. That's a very long, it's a slow process, but it's a notable one. And the reason I bring that up is there is a global drop in climate change that is associated with the uplift of the Himalayas or the Himalayas. You can pronounce it either way. The Himalayas. Let's call the whole thing off. Anyway, the point being, as the Himalayas are uplifted, as Mount Everest is uplifted, you have a drop in global temperature, and it's because of that uplifted ocean rock, that marine rock, interacting with the atmosphere and removing carbon dioxide from the Earth's atmosphere and then sequestering it down below in ocean sediments, deep ocean sediments. So this is another way that plate tectonics is affecting global climate. But in this case, number one, it is cooling global climate. And number two, it is doing it over tens of millions of years. It's not a warming effect that we're seeing just over the past few decades. So here too, we aren't seeing that plate tectonics and the uplift of the Himalayas or the Himalayas, is having any particular effect that would explain the pattern that we're trying to explain. Plate tectonics is also responsible for Antarctica being parked over the South Pole, and so it is a land mass, which means snow and ice and glacial ice can form there, whereas in the northern hemisphere, in the North Pole, there isn't any dry land there, so you don't have the same potential to have ice forming there. Now, what else can we look at? What else can we study? Well, this is looking at a diagrammatic representation of the Pacific Ocean. And you can hopefully see over there on the right, you can see the bottom half of North America. You can see Baja California. You can see a tiny little bit of South America there. And then over on the left, you can see Indonesia. And so this is the normal condition in the Pacific where you have the trade winds cycling more or less clockwise in this direction. And so you have rising moist air in the west, and then you have high rainfall in that area, and then descending dry air in the eastern part over here next to the Americas. But what can sometimes happen is what's known as an El Nino, where the rising moist air moves towards the middle of the Pacific Ocean because of moving, shifting, warming masses of water. And so you develop, instead of rainy conditions, you develop drought conditions in Indonesia, and you can have quite a bit of rainfall here. You can have a change in climate here. So this is also a contributor to global climate change. But we do have El Nino years mapped out, and they are not corresponding with the warmest years on record that we're observing. I did mention that 1998, which for a time was the warmest year on record, was also an El Nino year. And so there was some discussion at the time about whether El Nino might be contributing to the overall pattern. However, that was 1998. That was ages ago. And as of now, there is no direct correlation between the warming patterns that we're seeing, that we're trying to explain, and the El Nino phenomenon. And this brings us to leaving the Earth's surface and looking at the Earth as a whole, and what are known as Milankovitch cycles. And again, I'm going to test you on these, so I want you to keep these in mind. There are 3 Milankovitch cycles, and these all have to do with the relationship of our planet relative to the sun and relative to the rest of the solar system. The 3 Milankovitch cycles that we're going to talk about were first discovered, or at least described, by Milutin Milankovitch, and so that's why they have his name. And they are orbital eccentricity, axial tilt, and precession. And we're going to look at each of these. Orbital eccentricity means that and by the way, I've got to apologize for all the snuffling and coughing. I'm still having a massive allergy attack. I haven't gotten over it yet. And so I apologize. This is probably uncomfortable for you to listen to. Believe me, it's uncomfortable for me to deliver, but I'm going to try and get through this before I need to blow my nose. Anyway, orbital eccentricity varies, where at some points when the Earth is orbiting the sun, our orbit is more or less a circle held in place by gravity. And then that changes through time, and the orbit becomes more elliptical. Now, these are just diagrams. These are diagrams showing the phenomenon. If you were actually hovering above the solar system in outer space, number one, it'd be very hard for you to even find Earth. And number two, the variations in eccentricity are not nearly this dramatic. They're much smaller. But what is essentially happening is that Earth is getting a little bit of a tug from elsewhere in the solar system, specifically the planet Jupiter, which, even though it's tiny compared to the sun, it is sufficiently massive, and its gravitational force is so strong that the Earth does feel it, and the Earth is pulled just a little bit out of true. But it cycles from more circular to more elliptical, back to more circular. Okay, when it is circling and it's more or less a circle, then the Earth is more or less the same distance from the sun all year long. When the orbit is more elliptical, there are periods during the year when the Earth is closer to the sun, and periods during the year when the Earth is farther away from the sun. And as you can imagine, the closer you get to the sun, the more intense the solar energy that the Earth is receiving from the sun, right? It's like getting closer to a flame or pulling away from a flame. The closer you get, the more energy you feel, the more heat you feel. It's the same thing with the Earth's eccentric orbit, where if it's a little closer to the sun, it's going to be receiving more direct and more intense solar radiation. When it's more nearly a circle, that radiation is going to be more evenly distributed over the course of the year. And so this contributes to seasonality. This is contributing to the strength of our seasons. How strong is our summer? How warm is our summer? How cold is our winter? And so on. Okay? And this pattern takes place over about 100,000 years. So the cycle from more circular to more elliptical, back to more circular, takes place over 100,000 years. So it's a much faster process than what we've been talking about so far, where we talk about plate tectonics and we're talking about millions of years. But it's not decades. It's not talking about a short period of time over just the past few decades. This is a 100,000 year cycle. Okay? Now, It's just one of the Milankovitch cycles. The next one is known as axial tilt or obliquity. And as you've probably seen throughout your life, if you've ever seen a globe, like for in school or at home or for sale in the store, they're almost always tilted. And that's because the Earth is tilted relative to what's known as the ecliptic, essentially the plane of the solar system, where most of the planets are all pretty much on the same level, the same plane. They're on the ecliptic. And the Earth is tilted, the Earth's axis is tilted relative to that, and that's known as axial tilt. And that tilt changes through time. This is why we talked about earlier with seasonality during some times of the year when the northern hemisphere is tilted towards the sun, it receives more intense solar radiation. In some parts of the northern hemisphere, the sun never even sets, whereas during those same periods, the sun never rises in some parts of the southern hemisphere, and so you can have extremely chilly temperatures there. And then that reverses itself as the Earth moves around the sun. Suddenly, the southern hemisphere will be more exposed because of axial tilt, and it will be getting more direct radiation, and the northern hemisphere will be cooler, which is what we are doing right now. We are moving into winter. We are moving into a period where we will be tilted away from the sun, and the southern hemisphere of the planet will be tilted towards the sun, and they will be experiencing the hottest temperatures of the year for them. That's because of axial tilt. And axial tilt also changes through time from a deflection of about 24.5 degrees to a lesser deflection of about 22.1 degrees and then back. And by changing that, you can see how just that little bit of change is going to change the solar intensity of the energy reaching either the northern hemisphere or the southern hemisphere. When it's tilted more strongly, it's going to be receiving more direct radiation. When it cycles back and is less tilted, it will be receiving somewhat less direct solar radiation. And this cycle from more inclined to less inclined relative to the ecliptic, relative to the sun, takes place over about 40,000 years. So it's not in sync with the orbital eccentricity, but it also isn't something that's happening over the course of just a few decades. Finally, there is the phenomenon known as precession or wobble. And if you've ever played with a top where you pump it up and you let it spin, and then you watch it start to lose energy and it starts to wobble, that is essentially what the Earth is doing on its axis. This is different from axial tilt. It is wobbling on its axis. And this takes place over a period of about 26,000 years. And I want you to keep this in mind because right now, if you ever get lost in the desert and you don't have a compass with you, you can always find north by looking for the North Star. And if you know how to do that, you look for the Big Dipper. It's an easy constellation to find. And you look at the outer two stars of the cup of the Big Dipper and you draw a line through them. It's going to point to the North Star. And you do that, you found north. Now you've oriented yourself. Now you can hopefully figure out which way to go. Don't try that 13,000 years from now. Because of precession, the North Pole is not going to be pointed at the North Star in 13,000 years. It's going to be pointed at the star Vega in the constellation Lyra. That will be the North Star. And then after another 13,000 years, it will cycle back, and Polaris, the North Star, will once again be our North Star, and you'll be able to find your way in the desert again. So keep that in mind. 13,000 years from now, don't go looking for the North Star because it's not going to help. The point being, this is also a 26,000 year cycle. So it doesn't line up with the orbital eccentricity cycle, and it doesn't line up with the axial tilt cycle. They're all fluctuating in different ways and at different times and in different manners. And this is contributing to the amount of solar energy that reaches the Earth and to seasonality here on the planet. And so when we look at these and you see that squiggle down at the bottom of this diagram, what you can see is variations in solar energy that are a combination of these three cycles. The key thing is here, these are definitely contributing to global climate, absolutely contributing to global climate, but not over a period of just a few decades, which again is the pattern that we are trying to explain, that we are trying to figure out what's going on. We have one hypothesis so far that's working. This one also doesn't work because the timing is wrong. This doesn't work over the period of a few decades. This is working on millennia. And in fact, it's been argued that we should have been moving into a cold period by now based on the Milankovitch cycles. And clearly, as you've seen from the data that have been presented in this class, that is absolutely not the case. So, possible causes of recent global climate change include greenhouse gas emissions from fossil fuels. We talked about that at length last lecture. Milankovitch cycles we just talked about, and they don't match the pattern. Solar energy output fluctuations, that doesn't match the pattern. Plate tectonics doesn't match the pattern. Volcanism doesn't match the pattern. Ocean currents doesn't match the pattern. None of these explain the pattern. There is only one hypothesis out there that actually fits the data, and that is greenhouse gas emissions caused by human activities, mainly from fossil fuel combustion. And so, again, I want you to be aware of this. I will test you on this. I want you to think about the fact that there are some people who will insist that there's no way we can be controlling the climate. We aren't. All of these other factors are still affecting climate as well. All of these are still in play, but they aren't causing the pattern that we see. It's like a change in the recipe where if you add too much salt to a pecan pie for Thanksgiving dinner and you end up with a salt, excuse me, you end up with a salty pecan pie, it's not because the other ingredients weren't in there, it's because one of them was out of whack. And it's the same thing with what we're seeing now, where something is out of whack, and the one that fits the pattern that we're looking at is greenhouse gas emissions from the combustion of fossil fuels. Now, it has also been argued by many people, and as I touched on earlier, that it has been warmer in the Earth's past. It was warmer during the time of the dinosaurs than it is now. Absolutely true. And in fact, if you go back hundreds of millions of years, you can see some amazingly warm periods relative to where we are today. That's where we are today. And you can see those little red dots there for 2050 and the year 2100. Those are projections, but they're nothing like some of those wild spikes in heat that you see over there on the left of the graph. Like right there, at the end of the Cretaceous period, or near the end of the Cretaceous period. This is the time of the classic dinosaurs, and you can see that there's a much bigger spike in global temperatures there based on the available rock record than what you're seeing today, even with the projections that we are seeing. And that's not even the maximum. Over here, at the end of the Paleocene epoch and the beginning of the Eocene epoch, is a spike in global warming, an amazing spike in global warming, that is referred to as the Paleocene-Eocene thermal maximum, or PETM. I may very well test you on that. I don't know yet, but you should probably write it down and remember it, and see how warm that is. And so the argument that has been made is, well, if it was so much warmer in the past, then why is the current warming that we're looking at such a big deal? Why are we so concerned about it? And as I believe we've touched on, it's because our development as agricultural societies and as civilizations has been constrained to about the past 10,000 years or so, which has been climatically a very stable period in terms of climate. It's only in the past few decades that it's gone haywire. Okay, so all of the things that we've done, all of the agriculture that's been invented, the civilizations that have developed across the globe for millennia, is based on a relatively stable climate pattern for the past 10,000 years. Think about all the organisms and ecosystems we talked about. Think about the biological interactions between different organisms. We talked about phenology and the importance of pollinators and plants lining up correctly so that they can effectively reproduce. Those relationships are all dependent on that amount of climate being relatively stable over the past 10,000 years. And that's what's being upset now with the spike that we are seeing. Humans spreading across the planet, moving into different areas, developing agriculture, developing civilizations, all of it is based over the past 10,000 years, up to and including our current industrial society. All of it is based on that, and it's just the past few decades that are out of whack, which is the pattern that you see here. So, what we're looking at is an explanation. The only one that works, the only hypothesis that fits the data is greenhouse gas emissions from fossil fuel consumption. You can see that here. There's the stable area that we're talking about, and over there on the right, moving up, you can see the projected um, warming based on whether we have low emissions, medium emissions, or high emissions. One more thing, I think only one more thing, maybe two more things. We've talked about the Earth, and from space it looks like this, and that's an awful lot of white cloud cover that you see there. And clouds do absorb heat, but they also reflect heat. And it's a phenomenon known as albedo. And albedo is the measure of the fraction of light that can be reflected by an object or a surface. A brighter object will reflect light, while a darker object will absorb light. And as you can imagine, you're seeing an awful lot of light colored stuff there, so it is reflecting a lot of energy, which is going to collectively keep temperatures less than they might otherwise be. Here's the albedo scale where 0 is pure black and 1 is pure white. So you can see that snow on ice is 0.9, so it's almost pure white, and so it has a very high albedo. Soil is generally dark. It's got a low albedo of around 0.2. The ocean is also dark, and so it's got a very low albedo of 0.06. Sea ice is not as bright as snow on ice or land-based ice, but it still is bright, so it's got a albedo of about 0.6, right? Makes perfect sense. The higher the albedo, the more reflective the substance is and the more energy being radiated back out. With that in mind, let's look at what's happening in our part of the northern hemisphere and in other parts of the world as well, depending upon which part of the earth is tilted closest towards the sun. And what happens when snow cover like this, which, as we just said, has a high albedo, when you have temperatures rising globally, you have an impact on this system and you start to have this snow melting more and more. And as it melts, it exposes the soil underneath, which, as we mentioned, has a low albedo, closer to 0. And so it's absorbing more energy, which is going to increase the snow melt, which is going to expose more soil, which is going to retain more heat, which is going to increase the snow melt. And so you start a cycle where you're losing more and more ice and snow because of the loss of albedo and the increase in dark areas, whether on land or in the ocean, being exposed to solar energy and trapping that solar energy and causing an overall warming phenomenon. And that's not just true for ice and snow at the surface, it's true for ice and snow below the surface. This is a feature known as permafrost. Probably poorly named because, as we are learning now, permafrost is not permanent. If you raise temperatures enough, which is what's currently happening, you start to lose the permafrost, it starts to melt. And so when you have plants at the surface taking carbon out of the atmosphere, photosynthesizing, taking oxygen in and releasing carbon, there's also carbon stored in those sediments. As you heat things up, the plants are releasing more old carbon into the atmosphere, which is a net increase in carbon. As the plants continue to grow, the albedo continues to drop. You have more carbon going out than coming in as things thaw. This takes place over decades, but it is the pattern that we are seeing now, where as you start to lose permafrost, you start to increase the carbon dioxide in the Earth's atmosphere. And so I actually kind of like permafrost because what happens with permafrost as it melts is you start exposing ice age animals. And this is a colleague of mine, Aisling Farrell. She's the collections manager at the La Brea Tar Pits. And here she is working up in the Yukon. And that is an ice age horsefoot that has just been exposed by melting permafrost. So it's a good thing for paleontologists who want to study the ice ages because we find all these fossils, but it's part of a larger pattern, which is a warming pattern for this area that is not necessarily very good. I'm also studying some horses up there. I have to take this picture out because this picture was taken back in 2017 or 2018, and we still haven't published that bloody horse. It is an Ice Age horse that was preserved in permafrost and exposed as permafrost was melting. You've got a skull, a lower jaw, some limb bones, and it was very exciting back then, pre-COVID, but we still haven't published it because we're not sure what we want to say. So I should probably take this slide out. Anyway, the point being, as you increase temperature, you have an increasingly green Arctic region. And that sounds good because you have more growing vegetation, which sounds wonderful, but you'll also have the melting permafrost. And so the vegetation above ground is a carbon sink, right? It's storing the carbon, but below the ground, as the permafrost melts, you have a carbon source, and it's releasing more carbon than is being retained by the growing vegetation. So you have a net release of carbon into the Earth's atmosphere. In the southern hemisphere, down in Antarctica, it's mostly ice, so you don't see the same phenomenon. Uh, in the northern hemisphere, in the North Pole, as I mentioned, you don't have dry land. So the snow and ice that forms there isn't forming on land, it's sea ice. And this has been showing a pattern as well as it continues to melt. And what you're looking at here, this is from 1984. This is a model from 1984. And the whiter the snow you see here, the longer it has been around. You can see that in the bar graph down there in the lower left, where the whitest ice that you see represented is ice that has not melted over the course of the year, and it has lasted in place for more than 4 years. It's not melting during the course of the year. But if you compare that to today, 2016, you can see that the vast majority of the ice is not making it through the year. It is actually melting. And so you've only got a very tiny fraction of the North Pole ice that is actually remaining for more than 4 years. And the bulk of it is only surviving for about a year or two before it melts. And so this is the pattern that we are still observing today, which means for those of you who are getting ready for Christmas, maybe coal is not the best thing for stockings. Maybe something else. Don't worry, I'm sure Santa has a backup plan, but that's for Santa to figure out because that's what he does. That's also Christmas, and we aren't there yet. We have another major holiday coming up first this week. For those of you who celebrate, I hope you have a good Thanksgiving. For those of you who don't celebrate, I hope you nevertheless take some time off and enjoy some time with your friends, with your family, with your loved ones, and have a good rest of this week and a good weekend. And we'll pick up where we left off next Tuesday, not this Thursday, obviously, but next Tuesday with our one or two more lectures, and then we'll be done. And then it's final season, and we're out. Okay. Any questions? Feel free to reach out. Chances are good I won't answer them on Thanksgiving Day, but other than that, if you have questions, let me know. I'll do my best to answer them. Until then, take care of yourselves. Have a good rest of the week, a good weekend, and we'll talk to you soon.